Hello, I'm Saidaoui. I'm a postdoc researcher in the Department of Mathematics in RWTH Aachen University in Germany. And today I want to talk about Deep Nurbs, which is a physics-informed neural networks which we implement to solve PDEs in complex geometries. So starting by the outline of the presentation, so I'm going to start with an introduction, then I'm going to shed the lights on admissible fields. Then I'm going to talk about what we call the admissible neural networks, which is the same as the Deep Nurbs. And in the first section, I'm going to show the results that are that we obtain after the application of this new approach to various type of problems with complex geometries. And finally, I'm going to conclude. So starting with the introduction, I'm going to start directly talking about the physics-informed neural network. I think this is of my interest to my presentation. So the PINs, or the physics-informed neural network, is seen generally as an unsupervised way of solving the forward and inverse PDEs related problems, right? So I say unsupervised because for well-posed problems, accept the fact that we need the boundary condition data. Usually for the forward problems, we don't need additional data in order to have a solution for the PDE. So that's why we call it an unsupervised approach. So instead of what is the offset then? So instead of using the data, we impose physical constraints or physical laws, and this will be our alternative to the collected data. So in order to get more insight about the PINs, we shall make a small comparison between it and the classical neural network, right, which is based on the data. So the classical neural network is based on the data. So given, usually we would have like pairs of data where the input is a d-dimensional array, d-dimensional vector, and the output for the regression problems is a real number. What we are looking for in the classical neural network is to find a map, whatever the problem is. So we are looking for a map F that matches or that approximates the relationship between the output Y and the input X. So then we can define it as yn equal f of xn plus epsilon n, where epsilon n is an error, which is associated, for example, to measurement error or to any kind of errors. And in this case, we simplistically model it as an additive error. Okay, so given that, we can see that our approximation or our mapping can be given as the expectation of y given x. Okay, so this is for the classical neural networks. For the PINs, instead of having or dealing with the data, we used we are using the boundary data, right, plus the physical constraints or the PDEs. So the mapping is given by the output y given the boundary condition and the PDE. Okay, so coming now to what is schematically or the process of optimization in both approaches, right? So both are machine learning models, so they are based on an optimization process, right? Wherefore the classical neural network, we have an input and an output. This output is a labeled output, right? And we have a neural network here where we have the parameters, variables here are weights and biases, and we use optimization, or we just like optimize the loss function associated to this architecture in order to extract the weights and the biases. Okay, so this is for the classical case where the mean squared error or the loss function is given as follows, as the difference between the estimator applied to the training points minus the true value. Okay, squared. So this is the classical neural networks. However, the things with the physics-informed neural networks are a bit different, right? So first, talking about the loss. So the loss now collects many terms, many different terms, mainly the boundary conditions, right? Plus the new thing is the physical laws or the constraints, right? And that's what is put here, right? So this is the main difference. And in addition to that, we should mention that the physical laws or constraints which all the time have derivatives with different orders. So these derivatives are calculated within the neural network itself with using the backpropagation or what we call the auto differentiation. So that's what makes these physics-informed neural networks a kind of robust framework, because even the derivatives or the derivatives or for any order can be calculated not numerically but exactly using back propagation. Okay, so the pins has been applied lately to many problems and was interfering with many fields, right? So these kind of very well-known problems were ranging from the burgers problem solved in the paper of Racy. We have an interface. We have as well the application of the pins to fluid mechanics, to the optics as well, and for different kind of problems, for variational problems, we have the dip rates as well for, and this one is of interest in our case because we are using the variational or the energy, the minimization of the energy in our loss function. So we are using a scheme which is comparable to the scheme used in this paper. So now we are going to talk about the admissible fields, right? So the admissible fields, which is a way to construct the geometry, right? It's based on the B-splines, which are the basis functions, right? So the B-splines, which are the basis function, defined as n of IP. So n of I0 is defined as follows, where the n of IP, which is the n number I with a polynomial of the order P, is defined recursively as function of other basis functions with polynomial of degree P minus 1. So this basis function is dependent on the parametric space variables, which we call here eta. And this parametric space variable defines the parametric space itself. So one of the directions of the parametric space is called the knot J, is defined as a vector of ranging from 0 to 1, where we have several junction points in between, right? So this is mainly the basis functions or the B-splines that we use in order to construct our geometry. And for our geometry now, the way we construct the geometry or the variable in the physical domain. So the x or the variables in the physical domain are given simply by a tensor product between the basis functions of index I against the ones of index j, multiplied by what we call the control points, Pij. So here it is a two-dimensional case where the control point Pij it's multiplied by Pij, but this one is, as you can see, is divided by a weight. So this weight is as well tensor product of polynomials. That's why we should have, so that's why it's called the rational. So if we want to talk about the name NURBS here, so it's non-uniform because of the fact that usually the spacing here is not uniform. So here the R stands for the rational, and the other one is B-spline. The rational because of the fact it's normalized over this weight, okay? And this weight is a polynomial as well, okay? So with the same way that we construct the real space variables, we construct our admissible fields. Admissible fields, the one that we are looking for, which depends on the parametric space. This is given by the same way as a tensor product of base function multiplied by scalar function phi. So the scalar function phi, we can think of it as a z component, a third component of the control point. Okay, so this is an illustration of the geometry and of the admissible field as well. So here the ones nodes in white, these are the control points. If you see here, we have like 3 by 3, 9 control points, right? And here is another control point. So the height here is defining our admissible field, right? So if you see the analogy here, we can see that this is the one in the middle having the highest, is having the highest attitude here. So it is exactly having the highest value here, right? So the phi or admissible field is the height or the amplitude of this control point. And that's what makes it very useful in our case, because here we can automatically impose our boundary conditions, right? So the idea here is actually to impose the boundary condition and not to just like use and not to use the boundary condition points in order to impose this, but to impose it using an external function, which is the NURBS here, the admissible field. What is inside here, except this boundary condition, we expect it to be a smooth function since it is given by polynomials. And then we expect that our neural network will adapt to this one and will adapt to the PDE itself. So this is globally, this is what we are looking for. And the main point here is really to impose the boundary conditions, the Dirichlet boundary conditions in this case. So that's now coming to the admissible neural networks, which is a combination that we are looking for between the admissible fields that will impose our boundary conditions and the neural networks which solves the PDE. Okay, so this is an illustration of the process, right? So we would have the data. So here it's we don't use any supervision, right? From data point of view, I'm talking. So there is no data, labeled data. Even the boundary conditions, we don't use labeled data. So what we have here, there are points where we are starting our optimization, right? And we have a neural network. So here, our function, neural network function, u bar of theta of x, is given as a complex function embedded nonlinear functions of our input d-dimensional vector, right? Okay, so what we have in the other hand, we have our loss function that we will see in a few minutes. So this is our loss function, so which is the energy loss function, right? And what we want to do is to solve or to minimize this. Okay, given that our solution is given by the product between this neural network function and the phi, which is the admissible field or the NURB. Okay, so this is what is a kind of what is the new idea here is to have a NURB, to have a neural network multiplied by another function, which is the NURBS, which will impose the boundary conditions. Okay, so then the NURBS or the output or the input of the NURBS should be the admissible field and its first derivative. In this case, that we have only first derivatives, right? So this is a Ritz method where we transform higher order derivatives to just like a function or an energy of only first derivative. And we need the auto differentiation of the neural network function as well. So that's what we do here. So the process is as follows. We input the admissible field and the gradient. This one won't change anymore, and this is fine for us because this one just like has or memorize the boundary conditions, and that's very enough. The other work will be done with by the neural network with itself. So this is just like a one-time input, and all the process will be here. All the process will be here, trying to minimize this one, trying to minimize this energy term. Okay, so in the following examples that we are going to go through, we are interested in solving the Poisson equation in 2D. Okay. Actually, the f of x is equal to 1 in our case, and the x is a d-dimensional vector, and omega spans the physical domain. Delta omega is the boundary. So the above function, if we use the Ritz method, can be transformed to an minimization of an energy term, which depends only on first order derivatives, right? And plus another term. This term is the term that will take care of the boundary, right? So this term usually and this is what has been done in the Dirichlet paper work that they have shown you in the previous slides. So this term is the one that imposes boundary conditions. However, in our case, we're going to see that this term, we don't need this term anymore, and we'll see why. Okay, So in our case, the U of X theta, so the solution to the PDE, is given by a product between the neural network function multiplied by the admissible field, right? So where the admissible field or the NURBS function contains constraints on the boundaries. Okay, the neural network approximation is given for the one hidden layer by this expression. So it's the sum of beta k multiplied by a nonlinear function multiplied by the weights of the weights multiplied by our input plus b. So here, why I put the one hidden layer, because mostly, and this is one of the good things that this framework, the good things done by this framework is the fact that most of the problems we only need one hidden layer to get a very accurate result, right? So this is for one hidden layer, this is expression of our neural network function, right? However, in the general, for L hidden layers, our network function will be b beta, which is a vector of amplitude multiplied by z theta x plus b, where the z theta is kind of an embedding of, or just like a function of another function of until you go to the first layer, right? So it's the L of the L minus 1, you go to the L z1 of x, right? And ZL is a sigma, which is an activation function or nonlinear function of omega L multiplied by ZL minus 1 plus BL, right? So this is the well-known relation between the ZL and ZL minus 1. And we have the dimension here of the weights and the biases. Okay, so given the fact that our function is given by the product between the neural network and the admissible field, and knowing that our aim of using the admissible field is to remove the boundary condition or to incorporate automatically the boundary condition. So the phi of x in the boundaries is equal to 0. Then the solution u theta will minimize this one instead of the previous one. So there is no term of the lambda term. Okay, sorry. So yeah, we get rid of this term, right? And we believe that this term is the one that makes most of the computational cost of the minimization of the loss function, right? So this is more costly than the other term. Okay, so we are looking to minimize the energy functional. Given that, so the expect, okay, so yeah, minimize the expectation of the energy function. Given that our x is, so we transform the integral to an expectation, given that our x is following a uniform random distribution. Okay. Practically, we use Monte Carlo to do that. So we transform the expectation or the integral to a summation of these terms. For many of the problems, we use importance sampling, right, in order to make even the calculation or the optimization with less variance. Right, where for the important sampling, the minimization should occur is of the function 1 over m, the sum over L theta of xi, where this is L theta of xi. So here, yes, this is L theta of xi. We divide it by rho of xi. So rho of xi is a probability distribution chosen according to an adequate importance sampling scheme. So now coming to the results, right? So just general settings of the numerical implementation. So talking about the neural network environment, we are using TensorFlow, and the activation function we use is max 0x cube. We use the Adam optimizer with learning rate lambda equal 10 minus 3. The number of layers for other problems, mostly one. In one problem, we use 2 layers, and the number of neurons per layer is 50. Okay, but I want to emphasize here that these parameters are not a result of a hyperparameter optimization, the usual way the machine learning problems work. But these parameters are valid for all the problems. I mean, we didn't use any hyperparameter optimization, and this is due to the fact that the physical constraints that we impose, either the pins physical constraints, I mean the PDE and the residual of the PDE, or the physical constraints, the new physical constraints coming from the satisfaction of the boundary conditions by the NURBS. This makes the optimization way efficient, and we don't need to play with this hyperparameter in order to get something readable or plausible. Okay, another thing, so I want to emphasize as well, is the fact that the scheme is totally unsupervised. Even the boundary conditions, we don't take them into account. I mean, within the neural network, and this should be very efficient if we want to apply this to practical problems. Okay, starting with the first problem. Actually, what we are looking for, or what we are interested more here in, is in problems where the geometry is presenting a lot of singularities, or is complex, having a discontinuity, because it's well known that the discontinuity caused a lot of problems, trouble, and needed all the time much more computational effort, even for classical solvers when we have a discontinuity. So all the time it's demanding more basis functions and finer meshes. But here we want to see to show that the application, or the Deep Nurbs, which utilizes the NURBS, which takes care of the boundary conditions, this one will help even with very tough geometry with very sharp discontinuities. Okay, so the first problem here is the known problem of the Poisson equation with corner singularity, right, as shown here in the figure. So we have a square where the points, the physical domain is all the square except this region, the 0, 1, from 0 to 0, 1. So this line, I just like put a cone. Some people assume it's a small cone, but this is only for illustration. But it's just like we are excluding this line, this half of the line. Okay, so this is the problem we are interested in, and this is the problem solved by Dirichlet's original paper, where they used ResNet with I think 4 blocks, right? But what we do here is we use the NURBS here and apply the Deep Nurbs framework, and we use only 1 and 2 layers. Right, so this is our phi, which is our admissible field. Right, this is before the application, before the use of the neural network, and this is L equal 1. So this is the solution using the deep NURBS for L equal 1. And this is the solution for L equal 2 compared to the exact solution here. So the as can be seen as can be seen from, I mean, the results for one hidden layer and for two hidden layers is resembles very well the exact solution. Also, we are using only very shallow neural network, and even more, although we are approximating of an equation in a physical domain which exhibits a very rough discontinuity, right? So this is the first problem we tackled, and here what cannot be seen here is the fact or the rate of convergence of the optimization problem. That's why we here plotted the training errors. So these are the training errors, right? So the blue and the orange and the green are the training errors for the pins, not the deep NURBS, the pins, the normal pins, right? For one layer and two layers and three layers respectively, right? With the same number of mini batches, with as well the same so for one layer, two layers, and three layers with the same number of mini batches, and the red and the purple lines are the ones of with the deep NURBS for L equal 1 and L equal 2. Here, actually, the rate of convergence are uncomparable. So here in the inset, I have plotted the logarithmic scale. When you can see the red, the black one is the normal pins, and the magenta one is the deep NURBS for the same number of hidden layers. So there are two hidden layers. As you can see, from 0 to 750 epochs, so this is the number of epochs, you can see that the normal pins doesn't is kind of static, doesn't improve, whereas the deep NURBS error goes to very small errors. It's almost 10⁻⁵. And this is due to the fact that the only reason for this is that the approximation of the boundary conditions, if we approximate them using the neural network, that will take too much time, and this is very costly. That's why we approximated them using the NURBS, right? And this kind of approach has been initiated by Lagares, right, many years ago. But the problem with Lagares is that the function he puts is a function that is that cannot generalize for complex geometries. That's why the NURBS comes here as a good solution for complex geometries. Okay, so this is exactly pouring into the same direction. So here we have the 3D errors, right? And so the three on top are the 3D errors for the deep NURBS, and the three on bottom are the 3D errors for the normal pins. As we can see here, so for epochs from 200 to 800, we have the deep NURBS errors are just like going to 0.02, where the errors for the pins method is just like kind of static, and it doesn't change, and it doesn't improve. It doesn't have the impression that it improves. And this is exactly similar to what I have shown in the previous slide, right? Okay, and this is our numerical values of the errors for the MIC and the relative error and the L infinity. So for all the type of errors, we have that the Deep Nurbs is giving a way better estimator for the solution of the PDE. Okay, so we believe, as I have said, that the trouble or the computational cost for the pins was approximation of the boundary condition, especially when you have sharp discontinuities, right? And using the Deep Nurbs or the automatic approximation of the boundary using the Deep Nurbs makes it very, very time efficient. Another thing here is the fact that we are using an inductive bias, right? Because we are multiplying the Nurbs with the function. So we are multiplying Nurbs with the neural network. So the neural network tries to adapt to the Nurbs and to adapt to the PDE to the PDE equation, to partial differential equation as well. So one of the things that we should notice here is that the fact if the Nurbs has a strong and inductive bias, that might affect as well the rate of convergence of the optimization. And we are going to see one example in the slides to come. Okay, so looking to see more examples here, we consider another example, a discontinuity analysis. So we have an analysis where we just like have the quarter of it. So we're trying to make more the discontinuity and to see how does this affect the convergence. So this is our phi, our admissible field. So this one usually in the applications, this one should be given I mean, this one should be given or should be calculated based on prior knowledge about the system, right? So here in this case, it is a guess. It's a simple guess, and we don't care too much about the values inside. The only thing we care about mostly the fact that it mimics the boundaries. That's the most important thing. Plus, we need it to be smooth. Given that this is the admissible field is a combination of polynomials, so we are very fine about it being smooth, right? And then the solution here in this case for this problem is for only L equal 1. So we use only one hidden layer, and you can see with the eyes that the similarity is so that the solution we obtain is very similar to the exact solution, right? And if you see the numbers, it's a sign of a very, very good accuracy of the solution. Okay, so going to the third and last example here, and here I want to show the point about the inductive bias, right? So this is another analysis, but it's not analysis, but another shape where it's not there is like a asymmetry here. So what we do in order to model this physical domain or this PDE. So here all the time in the three examples we use the Poisson equation, the same Poisson equation, but we change the physical domain in order to see the impact of the discontinuity and the impact of the choice of our admissible field. right? So here the admissible field, we choose it kind of having a strong inductive bias, like towards one direction here, which is not the right direction of the solution. And here is the solution. So for L equal 1 or for L equal 2, both they exhibit very good approximation of the exact solution. However, the only problem that comes here into play is the fact that the change or the rate of change of the error is slower than what we have before, right? So now the convergence rate is smaller. So here it's from 200 to 800. We are getting only 0.1, where in this case, for example, it's 1 order of magnitude better, right? And this is due to the fact that, so this is the solution, and this is the proposed admissible field. That proposed admissible field is having a kind of strong inductive bias, which doesn't affect the final solution, but affects the rate of convergence in the optimization process, right? So here we believe that we should have in order to have a very, very efficient optimization process or deep Nurbs, we should have an optimized admissible fields, right? So now the admissible field is based on guess. Actually, it works all the time like that, but I think incorporating an admissible field that is optimized, right? So the admissible field, which depends on the control points, optimizing the height of the control points can improve, I think, very well the convergence rate. Otherwise, for these different categories of problems that we have gone through here, just like a very shallow neural network was very good enough in order to approximate it. Okay, so here I wanted to show the last point about the inductive bias, right? So let me share. Okay. Okay, so this is a kind of a video clip for the solution, or just like a sequence of the solutions, just like I have calculated from epoch 0 to epoch I think 150, I think 150,000, something like this. No, to epoch 50,000. Yeah. So and it shows how the deep Nurbs work, and how the neural network tries to simultaneously tries to solve the PDE and to at the same time opposed to the inductive bias of the of the admissible field. Here you can see it. So here, this is the direction of the inductive bias here. So the neural network, it tries to just like, yeah, to oppose to this anisotropy, kind of anisotropy. And as I said, I think that optimizing the Nurbs from the beginning should give a better, even a better result. Okay, so back to our presentation. So we come now to the conclusion, right? So with the deep Nurbs or admissible field neural networks, problems with discontinuity can be approximated using only one hidden layer, and this is a good milestone in this case, right? So the deep Nurbs-based optimization has much higher convergence rate as well. So for few few number of epochs, we can have a good estimate, right? An amelioration of deep Nurbs is possible considering the optimization of the guessed admissible fields, and that should be of interest for future work. And that's the possibility of using admissible fields in higher dimensions. So it's possible to use the admissible field in higher dimension, which renders the deep Nurbs a prominent machine learning solver for partial differential equation. Okay, so yeah, that's all for the presentation of today. So if you have any comments or questions, please send me to my emails, which I have shown in the first slide. Thank you very much.